Swayam Prabha. Digital India. Educated India.
So what happens? It's very much like a cloud. The photons are unable to escape because they are constantly scattering with the water molecules. But when they come close to the edge of the cloud, there aren't many water molecules present, and thereafter the photons travels freely. And what you observe is the edge of the cloud, essentially. You don't see into the cloud. And that's your last scattering surface. Remember, you are observing the universe in different directions of the sky. So the last scattering surface is the surface around us. Okay? The surface around us. All right? And this is where you see the cosmic microwave background emanating from. And it carried imprints of what happened behind that. So the answer to your question is, if I observe the cosmic microwave background radiation, right, you will understand what happens behind that surface. Notice, this is the last scattering surface, and there is a Big Bang singularity. I hope you understand. As you keep looking in further and further in some direction of the sky, any direction of the sky, what will you do? You are looking at the universe as it was older and older, younger and younger, okay? Much earlier and earlier, all right? Therefore, there will come a time when you look in this direction of the sky, right? You will hit the Big Bang. But there is no reason why this direction of the sky is different from this direction of the sky. So any direction of the sky I look at, I will end up at the Big Bang singularity, and that is why you have a Big Bang singularity here. This is the surface of last scattering. What is our goal? Can we observe properties of the cosmic microwave background? That's my story today, to understand what happened behind the screen. Okay? All right? So I talked about it. I talked about the fact that there is a cosmic microwave background which has a temperature of about 2.725 Kelvin. It has two properties. Firstly, up to the third decimal place, the temperature of the cosmic microwave background is the same everywhere. Okay, it's called isotropic. Okay, so up till the third decimal place, the cosmic microwave background is very isotropic. Okay, so remember, if you have the surface of the Earth, which is very close to a sphere, the surface of the Earth has different temperatures, and I'm sure you have seen this picture plotting the temperatures on the different regions of the Earth. Sahara is very hot, as you can easily see. In a similar manner, this surface I talked about, it's just a sphere. The surface of last scattering is a sphere. I can indicate the temperature in different regions of the sky in the same manner as I indicate the temperature on different points on the surface of the Earth. And there are two things that you need to notice. First is the temperature in the different regions of the sky is almost the same, 2.725 Kelvin. But evidently it's not the same, right? There are different colors. Remember the old Penzias and Wilson picture. Okay, let me see whether I can go back. Here it is. It's almost the same, right? Remember I told you what this sky is. And do you recall what this horizontal line corresponds to? Very good. The galactic plane, essentially. Notice the temperature is virtually the same in all directions of the sky. In fact, from 1965 until 1990 or so, people were desperate to measure whether there are deviations in the temperature. Okay? Because, as I will describe, if there are no deviations in the temperature, you and I will not exist. Okay? I will try to explain that part of the story. I did using movies last time. I will elaborate on it. So, what is our goal? Our goal is twofold: to understand why the temperature is the same in the first place, and there are tiny deviations from isotropy. That is, if you look at the fifth decimal place, okay, if you look at the fifth decimal place, the temperature in different regions of the sky are different. And these are known as anisotropies. I hope you understand. The CMB is largely isotropic, but it contains small anisotropies. What is an anisotropy? Anisotropy implies the temperature in one direction of the sky is different from the temperature in another direction of the sky. And these are the anisotropies that have been plotted. Okay, and this was the first time these anisotropies were measured. As I told you, Penzias and Wilson discovered the CMB in 1965, and it was in 1990. Do you remember this COBE, Cosmic Background Explorer? It had an infrared image of our galaxy, right? And it was in 1990, the results came out in 92 or so. It was able to measure the anisotropies in the CMB, and cosmologists heaved a sigh of relief because until then, various efforts could not measure these anisotropies in the CMB. So what is the story about them? I'm going to again, skip some of these part. I answered some of the questions of dark matter. Something I'll just briefly mention before I go to this part of the story is the following. In the universe, there is ordinary matter that you and me are made of, but there is also something called dark matter. One of the simplest ways of convincing yourself this requires only Newtonian physics and nothing more is search on Google rotation curves of spiral galaxies. Okay? And assume a uniform density of matter. Correct? Assume a uniform density of matter, or density falls at a certain radius, okay, as a function of radius. It is not, okay, there are different ways you can model. You can assume it is uniform density up to a certain point, right? Up to a certain point here, all right? Maybe the density is not uniform. You attribute, it cannot clearly rise, it may have to fall. You construct different forms of rho of r. You understand what rho of r, what does that mean? The density of matter falling off distance, radius. And you think of, something going around, just use your centripetal force, equate it to the gravitational force, but they'll depend on the form of rho of r. Okay? And plot the velocity as a function of distance, radius. Kindly do this. This is not a big exercise to do. Now, what you find is that this is the thing expected from the visible disk. This is the curve expected from the visible disk, right? You can see, there is light emitted. Beyond that, there is nothing else. But you can observe there is hydrogen present in the universe. Remember, I told you earlier how hydrogen atoms were formed and so on, right? Okay, they get ionized later, but there is still neutral hydrogen present in the universe. There is an interesting story. It's a little complicated quantum mechanical argument, but I'll just tell you the story. There is a ground state of hydrogen. I'm sure you have understood the Bohr's atom model. Have you studied this? Okay. There is something called the ground state of hydrogen. The ground state of hydrogen happens to be split into two because of some complicated dynamics between the spin of the proton and the spin of the electron. Okay? And what it does is that it splits into two, and when you have two energy levels, there can be transitions between them. And there is an emission that occurs, which occurs in the 21 centimeter. The wavelength of that emission is 21 centimeter, or about 1420 megahertz. I would urge you to do that. Okay, it occurs in the radio region of the electromagnetic spectrum, 21 centimeter transition. There are many radio telescopes. Name one famous radio telescope in India. Where are they located? There is more than one. One is functioning very well, not quite. I don't know whether there is a radio telescope in Ladakh. No, LIGO is not the one. GMRT. Have you heard this? Giant Meter Radio Telescope. Okay, it's near Pune. Okay, it can observe from in Kodad near Pune. All right, it's called the Giant Meter Radio Telescope. It's run by the National Center for Radio Astrophysics located in Pune, and it can observe in the 21 centimeter. Okay, and when you observe, so there is neutral hydrogen present. Okay, and you can observe the emission in this 21 centimeter, and you plot, what is the velocity of that, whatever that source is, and you find that the rotation curve is like this. Notice this, it says this, observations from 21 centimeter hydrogen. All it does is that because of the spin of the proton and the electron, the ground state of hydrogen that you have learned from the Bohr atom model splits into two. When it splits into two, they emit photon as they make a transition from the upper state to the ground state, right? And the emission occurs in the 21 centimeter with a frequency, or rather wavelength, of 21 centimeter. And you can observe that using simple radio telescopes. Now, what you find is that instead of, if the matter was only in the visible region, this should have been the rotation curve of the galaxy. But the rotation curve observed from neutral hydrogen is this. Okay? It's called neutral hydrogen because the electron has to be present for this to make the transition. Is that clear? Now, this is usually attributed to dark matter. Dark matter does not interact with light. It interacts only gravitationally. It modifies the trajectories of this neutral hydrogen, which is emitting this. Okay? Whatever the source that is emitting in neutral hydrogen, it changes the trajectories. Evidently, the velocity is high, but it itself does not interact with light, and we are seeing its influence through the force law that I just through the Newtonian gravitational force and centripetal force that I mentioned about. Okay, so you now ask what should be the rho of r so that you obtain this curve instead of this curve. I believe this is an exercise for you to work out. And so essentially what you find is that galaxies are surrounded by dark matter. I briefly, in response to someone's question, talked about how you can easily see the imprints of dark matter through gravitational lensing, effects of dark matter due to gravitational lensing. So in addition to radiation and non-relativistic matter is something you and me are made of. I told you that cosmologists refer to this baryons. There is also dark matter present in the universe which you need to account for. And I talked about the presence of dark energy. I'm just going to spend 2 minutes on this, emphasizing what I had discussed earlier. You need to, in order to understand what the universe contains, you need to understand the deviations from the Hubble's law. Remember, the Hubble's law corresponded to plotting the velocity against the distance to the galaxies. Okay? So you need to measure, you need to understand whether there are any deviations from the Hubble's law as you measure galaxies to larger and larger distances. Remember, we talked about velocity, but I said we should not attribute a velocity to the galaxy. We should attribute only a redshift. And the redshift is a cosmological redshift. So you should plot actually distance as a function of redshift, as we will see. At small redshift or close distances, there is a linear relation, which we know as the Hubble's law. The question is, at larger and larger redshift, are there any deviations from it? This requires an interesting side story called a standard candle. If I want to measure properties of very far away galaxies, I need something very bright. Okay? I need something very bright. How do I measure distances? How do I measure distances? I cannot send him to Andromeda galaxy, and say, send me the, give him one edge of the, you see how people measure the sizes of rooms now. Have you seen these engineers come and measure? What do they have? They just have a laser beam, it reflects, comes back, and it measures, I presume, the time taken for it to get reflected and come back. So I can't send this student to, keep a reflector there, wait for 2 million years to measure the distance to the Andromeda galaxy. I can't do that. What do I need to do? I need to? No, redshift is just telling you something like velocity. It's not telling us distance. Very good. It's called, absolutely, it's called a standard candle. It's very simple. Okay? There are so many sources of light. And I'm sure all these lights have a standard wattage. Okay? It's probably 12 watts, right? And what it means, you know the power, intrinsic brightness of the source. I can always measure its brightness as I observe it from this distance. How does the brightness fall with distance? Flux falls with distance? 1 over r squared. Okay, you will learn about it in an electromagnetic theory in an advanced course. But this is what you need to know. So if I know, I keep a detector, a CCD camera, I measure the number of photons, I know its intrinsic brightness, I know the flux here. Do I know the distance? What do I need to know the distance, to determine the distance? The intrinsic brightness of a source, and that's called a standard candle. So there are supernovae. This is a supernovae appearing in a faraway galaxy. And notice it is as bright as the galaxy itself. Okay? Here is another supernovae. Notice this is the supernovae that has appeared and after it has faded away. So there is something called a light curve of a supernovae. Something explodes, the star becomes exceptionally bright and then it dims away. And the manner in which it dims and its spectra, we know there are different types of supernovae. We focus on certain types of supernovae. I don't know whether you heard, there was a Nobel laureate by name Brian Schmidt who had given a talk a couple of months back. I don't know whether any of you were present. He was talking about exactly this. So by looking at these supernovae of faraway galaxies, supernovae are exceptionally bright, which means I can easily measure redshift. We have discussed this. All I need to do is that I need to take the light from the star and compare, the light from a nearby star. That's it. Light from a faraway galaxy with the light from a nearby star. These supernovae allow us to determine distances to faraway galaxies because I know I can look at a close-by supernovae whose distance I know through other means. Okay? And therefore, if I know its peak brightness, I essentially know the intrinsic brightness, like this bulb is 12 watts. If I know that, I know the distance to the galaxy. And what people did, this is something I explained last time, I'm emphasizing again, is that, you can plot the luminosity distance. It's called a luminosity distance because I'm attributing a distance to the galaxy. Please remember, I'm not taking a ruler and keeping it to the galaxy. I can't do that. I am attributing a distance to the galaxy by observing properties of light. And what is the property of light we are observing? Its luminosity, its brightness. And you plot this brightness of these galaxies as a function of redshift. I'll come to you, just bear with me. And amazingly, what we find is that, I mentioned, look at this green curve. It tells you need a cosmological constant. Cosmological constant is a strange object. It is a density, right, which does not change with time. There is some strange object in the universe, even as it expands, right, as the universe expands, its density does not fall. What it implies is that it remains a constant. This is today. Okay, it remains constant, and it is roughly, in the total budget of the universe, okay, remember this is rho nr, this is rho cosmological constant. In the total budget of the universe, I need 70% as cosmological constant, okay, and this is not plotted very much to scale, but this is roughly the behavior. About 25% is in the form of dark matter. Leave that cold adjective now. If there are questions, I can answer. And the matter that you and me are made of, which we refer to as baryons, constitute less than 5%. Okay? All right? So I have 10 minutes to complete the part of the story as to how the anisotropies arose early in the universe. Quick question. Is already red. The light, we typically notice the spectrum you have seen, right? We observe over a wide range of wavelengths. Okay.
How do we distinguish light from another light which is redshifted into?
So we don't look at one line. That's the important point. Okay. So since you have asked this question, let me go to this line here. Okay. Let me see here. What I'm trying to say is that what you are asking is this. If there is one line I am observing, I don't know where this is. But the point is, there is a pattern of lines. And that pattern of lines allows me to determine how much is the redshift. So we are not focusing on one line, and that is what I want you to appreciate. Notice this, there is a pattern of this line. This emission line is present everywhere. Okay, so I use the pattern of line to determine the redshift. There is no issue. Okay, let's come back to the story. So the bottom line is that this pie chart, okay, there is something, there is a pie chart here. Okay, I have said 74, some numbers have changed, okay, since this pie chart was taken. All right, so you have about 70% in the form of cosmological constant, or sometimes it's called as dark energy. Right? And 25% is in the form of matter, cold, dark matter, and it's only 5% of the universe is made up of you and me. But this Big Bang model, what is the Big Bang model? That the universe had a radiation. It began in a hot, dense phase. There was radiation, and there was matter domination, and there was lambda domination, has a problem. And what is the problem? And the problem is that as follows. So have you seen these light cones being drawn in special relativity? Okay. The light cones being drawn in special relativity. Okay. This is X. This corresponds to a light ray which is moving in the right direction. This corresponds to a light ray moving in the backward direction. What you find is as follows. So there was a time where there was a Big Bang. So maybe I'll go to this graph. Okay. You can draw a light cone. There is a certain time of the universe. There is distance plotted along the horizontal direction. You can draw a light cone. Today, you can see how much was my past light cone. I hope you understand. If you are located here, everything within the light cone can influence you. And you can influence everything which is, in the forward light cone. So this is the forward light cone and this is the past light cone. If you are sitting here, there is no way you can influence anything that is happening here, because that implies you have to move at speeds faster than that of light. Now, there was a Big Bang. This was the Big Bang. Ignore this part for a minute. I'll come to that in a minute. There was a Big Bang. This is the time, this is the last scattering surface, which comes, from which the CMB comes to us. So you look back, right? You look at various regions of the sky, and you can look forward from the Big Bang. I can draw a light cone from some time to a certain time. What it implies is that this region would be causally connected. If it started here, this region would have been causally connected. Anything outside at this time cannot be influenced by something here. So invert one of these blue cones. So there will be a blue cone like this here. This was the Big Bang. There was a blue cone here, very much like that I have drawn. So what it means is that only this region of the sky could have been influenced. This region of the sky and this region of the sky would not have been influenced by each other, because that's the size of the forward light cone. The size of the forward light cone is like this. Okay? Like this. Like this. So what you are observing is the entire sky. They almost seem to have the same temperature. But if you ask, what is this forward light cone? I am drawing a forward light cone. What is the angle subtended by that in the forward light cone within this theory? I hope you understand. And that happens to be just 1 degree in the sky. Let me repeat. There was a time of the Big Bang, right? And there is a time from which the CMB comes to us from, and you can ask what is the size of the forward light cone at that time. Sorry. You can see this entire sky, right? And that corresponds to this backward light cone. There is a forward light cone, and you can ask what is the size of the forward light cone. It's a little non-trivial idea. I hope you're able to digest that. And that is just 1 degree in the sky within this hot Big Bang model. What does it imply? If there are regions of the sky which could not have been causally connected, what does it imply? Which essentially implies the temperature here need not be the same as the temperature there. If two objects have the same temperature, generically there is no reason for them to have the same temperature. If they have the same temperature, they should have interacted with each other. Now there is this universe, strange universe, and you have the Big Bang model. Within the hot Big Bang model, this patch in the sky, I shouldn't have pointed there, it won't work. Okay, this patch in the sky would not have interacted with this patch and this patch. In fact, there are many patches, close to 100 odd patches, more than 100 patches in the sky. In fact, more than 1 degree in the sky couldn't have been causally connected within the hot Big Bang model. This is called the horizon problem. Okay, in other words, the Big Bang model is not able to tell you why the CMB temperature is the same in different regions of the sky. If the temperature had been very different, okay, you would have believed in the hot Big Bang model. But there is a problem with the hot Big Bang model. So what you do is that one thing is very clear is that, remember, I told you this is the Big Bang. If I somehow push Big Bang to an earlier epoch, I push it behind, what will happen? This light cone would have been like this, right? But if Big Bang starts here, the light cone will be like this. And you can ensure that the forward light cone from the time of the Big Bang to this time, I hope you understand what this time is. This is like your satellite which has been observing the CMB anisotropies. This is the time. What is this time? What do we refer to this patch as? What do we refer to that particular surface as? The last scattering surface. That's where the photons are coming to us. So we are trying to observe the CMB to understand what happened behind the screen. But there is already a problem. There is no reason within the hot Big Bang model that this entire surface have the same temperature. Okay? So what you do is that you push Big Bang down. Okay? You go to, in some sense, negative values of time. Okay? And this can happen, I will tell you how. If you do that, it's clear, right? If instead of a light cone which starts from here, if I allow the light cone to start here, I can draw something which is much bigger than the backward light cone. And that's what inflation does. What it's been plotted here is time, plotted in this way, function as, this is the size of the universe, this is time. The universe is expanding. The scale factor, the size of the universe is expanding, is changing with time, it is expanding. This is the radiation-dominated epoch. This is the matter-dominated epoch. There is a sense of expansion. But if you have an epoch where the universe expanded extremely rapidly, okay, notice how rapidly it expands at a very early time after the Big Bang. So theoretical physicists, presumptuous enough to believe they know what exactly happened about 10 power minus 35 seconds after the Big Bang. And this is closely connected to particle physics. It'll need me a lecture or more to explain the connection. But I will explain very briefly in the next slide. If you have an epoch very soon after the Big Bang, where the universe goes through an inflationary era, what it means is that it goes through accelerated expansion. A is the scale factor, right? Whereas A appears somewhere. A double dot has to be greater than 0. It has to go through acceleration. Okay? If it goes through an accelerated expansion, the universe becomes very large. How big does the universe become? Notice, this is the size of the universe. It starts from something like 10 power minus 30 at the beginning of inflation in some units, okay, to about close to 1. So it has to increase by a factor of about 10 power 26 to 10 power 30 within what? A fraction of a second. Notice this is 10 power minus 35, this is 10 power minus 25. If this happens, you can explain why all these regions of the sky have the same temperature. And this idea is called the inflationary scenario. I'll skip these slides. What you do is that you can drive it. You need a special kind of field to create this rapid expansion. And these are called scalar fields. You can think of a ball rolling down a potential. There is only one difference as far as the expansion of the universe is concerned. There is a friction term. So what essentially happens is that there is a ball, which is your scalar field, which is present. And there are many such scalar fields in high energy physics. All right. And what happens is that the scalar field rolls down. When it is rolling slowly, the universe inflates. Okay. And if it is not rolling slowly, what will happen? There is a friction. It will make it roll slowly. Okay. So this slowly rolling field drives this accelerated expansion. What will happen as it comes down here? The potential is growing steeper and steeper. What will happen to this ball as the potential becomes steeper? Its speed will increase. As it increases, somewhere here, inflation ends and then the radiation dominated epoch begins. And there is something more amazing that happens. There was a question, how will I know what happened behind this curtain of the last scattering surface? These scalar fields are in high energy physics. I already mentioned to you, high energy physics involves, special relativity and quantum mechanics. In quantum mechanics, there are fluctuations. They are inevitable. Okay? In classical physics, if I say x is equal to 0, x squared is, any x power n is 0. But not so in quantum physics. Okay? You can have x is equal to 0, but you can have fluctuations. And these fluctuations are always present. There are many things that have been measured where the quantum fluctuations are, implications of quantum fluctuations have been measured. So there are these quantum fluctuations that are present, and it is these quantum fluctuations that are supposed to be responsible for these anisotropies in the CMB. So inflation does two things. What does it tell you? It tells you why these different parts of the universe have the same temperature. But amazingly, it also tells you why did these anisotropies arise. It gives you a mechanism for the generation of these anisotropies. So I talked about, this standard model of cosmology. And this is the part I didn't complete. I showed you some pictures to illustrate how these fluctuations arose, etc. These are the most exquisite measurement of the CMB anisotropies. The answer to your question is that by measuring this, we know what happens very early in the universe. And there are other observations, cosmological observations that are coming in. For instance, the distribution of galaxies in the universe, the manner in which they are distributed can help us understand what happened in the early universe. Okay? And this is the part of the story. I explained all this in the last class, in the last lecture. So this is the only part of the story that I could not explain in the last class. What happens is that there is an inflationary epoch. Okay? So in this story of the hot Big Bang model, I need to introduce an epoch of inflation during the early stages. Okay? This is the epoch of inflation. And it is this inflationary epoch that give rise to fluctuations. Okay? It is able to explain why the CMB temperature is almost the same in virtually every direction of the sky. And amazingly, it is also able to tell you why there are small deviations from the isotropy, which we refer to as anisotropy. I'll close, I'm trying to see where that was my timeline of the universe. Okay, I think it was earlier. I'll just use that slide to explain what we have. Here it is. This is a famous picture due to NASA. So the timeline, a brief history of the universe is as follows. You had a big bang, and then soon after, this curve here is supposed to tell you how the universe is expanding, the behavior of the scale factor A. There was a big bang, something very bright. We don't know what happened. Soon after, notice what is happening to the universe. It is expanding very rapidly. The size is increasing tremendously. And that's this epoch called inflation. And then you have an epoch of radiation domination. And this picture is the CMB, remember? All right? That roughly comes to you from this point here. After that, there is only, the CMB is not dominant. You have matter domination, but stars have not formed. And these are the dark ages. Can you see a dark patch in between here? And those are referred to as dark ages. And some point of time, stars begin to form. Okay? And this is called cosmic dawn, as I told you. There is cosmic dawn. And then stars begin to form. Galaxies begin to form. They merge, make this complicated structure that we see around us today. And notice there is a reasonable expansion. There is a slightly faster expansion during matter domination. And notice at very late times here, it is, again, expanding faster. This, the curve is sort of changing like that. That's because at late times we are dominated by a cosmological constant. And that also leads to an expansion of the universe, just like inflation. There are two epochs where the expansion is going through acceleration, and during the radiation and matter-dominated epochs, that the universe is not going through accelerated expansion, it is going through decelerated expansion. So that was one part of the story I had not completed. So that part is essentially that you have an inflationary, I already told you what is the standard model, 70%, 25%, and 5% of dark energy matter, non-relativistic matter, dark matter and baryons. And then I told you how inflation generates the perturbation, leaves its imprints on the CMB, and that's what I have said here, and gravitational instability. I told you even if you have small disturbances, they will end up forming galaxies and clusters of galaxies. And there are many, many observatories that are, there are ongoing observations and there are many planned observations. In fact, one of them, Euclid, top right, has started observing square kilometer array, SKA, will begin to observe the universe, okay? And dark energy survey is going on. And there are other, I haven't even included JWST here, okay? There are many, many observational missions that are planned or being, that are ongoing and are being planned. And you expect to have enormous amount of cosmological data coming in, and this is a good time to work on cosmology. And I will leave this slide for you to look at, and you can note these books. And these books are meant for popular readers. It's ideal for school children like you to understand where cosmology stands today. I'll stop here. Thank you for your attention. I'll be glad to answer one or two questions. Yes.
My question is a little disjoint from what you said
Mm-hmm.
in the lecture. But why is the solar system like roughly plane? Why not have more spherical solar systems?
Okay. So one good thing is that it's due to rotation. Why is a galaxy flat? Most of the many spiral galaxies are flat. What happens is that often there is some rotation. And rotation, what happens is that the moment there is rotation, nothing stops it from collapsing in perpendicular to the plane of rotation. But in the plane of rotation, there is a centrifugal force. Yeah? So many, many things are flat. Amazingly, the orbits of all the planets are very close to the plane of orbit of the Earth. The planes of orbits of all the planets are very close to the plane of orbit of the Earth, which indicates that, there was some sort of rotation which occurred under the planets form locally somehow.
Sir, so you said that the universe is expanding, right? So, and that has some kind of velocity attached to it, some kind of redshift attached to it, and some velocity attached to it. Now, for example, let's say we set out on a rocket from the Earth, and our velocity is less than that by which we say that our destination is moving away from us. So, will we ever reach our destination?
Look, you can estimate the time involved. It's a little complicated for me to explain this because of the fact that the universe is changing with time. But you can estimate, for instance, we know how much light is going to take, to travel from point A to point B, even in the presence of expansion. So in principle, yes, we can estimate the time it will take for me to travel from here to an Andromeda galaxy, accounting for the expansion. But often, since we haven't even gone beyond our galaxy, we haven't worried about that. Yeah? Thank you. Thank you, everyone.